All right, thanks, John and Debbie. Thanks to everyone for being here today. So today it is my distinct honor to introduce to you Dr. Steve Carpenter, who is the recipient of the 2019 AC Redfield Lifetime Achievement Award. This award honors long-term achievements in the aquatic sciences, including research, education, and service to the scientific community and society. Steve is Emeritus Director of the University of Wisconsin at Madison's Center for Limnology, and is also the Stephen Alfred Forbes Professor of Integrative Biology. He's receiving this award in recognition of his remarkable contributions to the field of limnology and lake management, including major advances in our understanding of trophic cascades, eutrophication, regime shifts, fisheries sustainability, and social-ecological systems via approaches that confront theory with large-scale collaborative experimentation, long-term lake surveys, and community outreach and education. So beginning with his first publication in 1976 from his undergraduate work with Stuart Fisher at Amherst College, and throughout his time at the University of Notre Dame and the University of Wisconsin at Madison, Steve's had a profound influence on aquatic science and ecology. He's pioneered and significantly contributed to many concepts that have reached beyond the disciplinary boundaries of limnology, and establishing him as one of the world's most influential and highly cited scientists in the field of ecology. Steve's known for approaching real-world ecological problems by combining theory and model development with whole ecosystem measurements and experiments. And an early example of this is the Trophic Cascade project, where Steve and his colleagues conducted a series of whole lake experiments to test the role of food webs in lake primary productivity, and challenged the idea that phosphorus runoff was solely responsible for the greening of lakes. From there, Steve and his colleagues have conducted numerous sets of studies pairing theory and experimental work to understand the significance of terrestrial subsidies of organic carbon to lake productivity, and to understand the complex patterns and drivers of rapid eutrophication. And since then, Steve has contributed even more big ideas to the field of ecology, such as the concept that critical thresholds exist for ecosystem function and the detection of early warning signs of ecosystem collapse. He's also combined environmental science with economics and sociology to help promote the study of ecosystem services and human well-being. So these examples just barely scratch the surface of the remarkable breadth, depth, and quality of Steve's contributions to aquatic science and ecology. And underscoring his accomplishments are his numerous prestigious distinctions, including membership in the National Academy of Sciences, recipient of several society awards, including ASLO's Hutchinson Award, and recipient of the Stockholm Water Prize, to name a few. And he's also the very first to unilaterally change his title without administrative approval to free-range scientist, complete with his own logo. So one last thing I want to say before Steve comes up, which is important, I think, to say, is I'd like to read a quote from one of his nominators, who says that even though Steve is a celebrated and true genius, he remains exceptionally accessible, humble, and sincere. He believes that you treat everyone on your team with respect and as a professional who can contribute in meaningful ways, and that science is a creative act that is best served when you follow your curiosity and find joy in the science that you do. So please join me in congratulating Dr. Steve Carpenter.
Thank you, Kim, and thank you, everyone, for coming today. I start the slides. Do I do that? Oh, there they are. I'm going to just give you a quick review of some recent projects that I've been working on. Awards are mostly about saying thank you. And in particular, I want to say thank you to collaborators and research teams that I have been fortunate to work with over the years. I would not be here without them. I also want to thank ASLO for having this awards program, and of course Dr. Redfield, who's shown here in this picture for his exemplary career. Okay, so the world is changing, and several speakers have already pointed that out, and I think everyone in the room knows it. I'm showing here one of the famous hockey stick graphs, and the red line, the thermometer-based records of global temperature show very clearly that it's getting warmer. This is a recent update of that graph from Terry Chapin's book that is coming later this year. No surprise here to anyone in the room. We've also got other hockey sticks. And this is from Will Steffen's famous paper on rapid change in the Anthropocene, and that was published a couple of years ago. And I realize the graphs are small, but if you look, say, at the orange ones, you see a number of things that are related to water resources. Fertilizer consumption, for example, construction of large dams, water use. All of those have big impacts on ecosystems that we're familiar with. So we don't have just one hockey stick. We have dozens of hockey sticks. We have enough hockey sticks to start a hockey league, but unfortunately there isn't going to be any more ice because of the warming. So we've got global problems here. Steep changes in drivers cause big changes in ecosystems, and the documentation to support this point has been increasing for the last 20 years or so. Probably the first well-documented case was rangelands, degradation of rangelands turning from productive grasslands to unproductive shrublands. And then there is also work on transformation of rangelands to deserts. Coral reefs are another famous example. Terry Hughes has done very influential and widely known work on collapse of coral reefs, some of them here in the Caribbean. And lakes, lake eutrophication, and also collapse of inland lake fisheries are well-known cases of big changes in ecosystems related to steep changes in drivers. Martin Scheffer and others have been very influential in developing resilience theory for these changes. The resilience network formed in the 1990s developed and applied a lot of these ideas to big changes in ecosystems. If you look at the high resilience system on the left, it's characterized by a deep basin of attraction. The resilience of that basin of attraction declines, it becomes shallower, and a number of discernible changes occur. Variance increases, you can see that in the graphs D and F that show variability over time. And autocorrelation increases. Graph G there shows, by the way, I apologize for not using the pointer, but this is the monitor down here, and I'm tempted to point them at the monitor, and then you're not going to be able to see it, so I'm just going to skip the pointing. The graphs G and H show the autocorrelation, the step correlation, and that correlation gets much greater as the resilience declines. The eigenvalue of a fitted ARMA model, which is a standard measure of stability, reaches or exceeds 1. You can think of the eigenvalue as a measure of system fragility. And when it's around 1 or above 1, the complex system is very fragile. And this theory has now been tested in whole ecosystem experiments, and lake ecosystems have been leaders in testing this theory. Here is an example from experimental eutrophication of Peter Lake on the left in this photo. Paul Lake is the reference lake on the right. And from 2013, 2014, 2015, successive levels of phosphorus and nitrogen enrichment were applied. The dashed horizontal line is where the eigenvalue is 1. The eigenvalue is simply an empirical fit to a time series model for the data. And you can see by 2015, the eigenvalue is hovering right around that very fragile value, which indicates a system that is about to change permanently to a new state. And these experiments have been written up in several papers listed at the top of the slide, and Mike Pace and Grace Wilkinson are here, so you can ask them if you want to know more about it. Lake Mendota in Madison, Wisconsin is a lake that I took my first sample from Lake Mendota in 1974, so I'm fairly familiar with the lake. The Center for Limnology is in the lower right of the air photo, and so my office is right there on the lake. Lake Mendota is surrounded by a watershed that's much larger than the lake. The pink on the map is urban areas. That's Madison, Wisconsin. And by the way, your next meeting, your 2020 summer meeting, is going to be in Madison, Wisconsin, on that narrow isthmus between Lake Mendota at the top and Lake Monona, the second lake there. So if you're interested in these ecosystems, you can go there in 2020 for a meeting, our meeting, and learn a lot about them. Those surrounding urban and agricultural areas are sources of lots of nutrients to Lake Mendota and the downstream lakes. Lake Mendota, the big one, is the headwater lake. We're getting more precipitation in Wisconsin, and that's true of many other areas. So here at the upper graph shows annual precipitation, millimeters per year, from 1940 to the present. And your eyeball tells you that there is a gradual increase with variability. That can be shown statistically as well, but I'm going to spare you the statistics. The statistical details have been published in Limnology and Oceanography in the paper listed at the bottom. For studies of extremes, the return level is a statistic that's often computed, and the bottom graph shows the 10-year return level of extreme daily precipitation. So what is the size of the 10-year daily rainfall, and how has that changed over time? And it has increased, as you can see from the graph, from 1940 to present. So we're not only getting more annual rainfall, the big storms are getting more frequent and they're getting larger. And these big storms bring things into the lake. They bring nutrients. Jen Tank gave a wonderful talk about that. They also bring large particulate matter, such as cars. Cars in lakes, drowned cars in lakes, do value as fish habitat, but they're unsightly and it's inconvenient for the owners, and we're getting a lot more of that in Madison and in many other parts of the world. Nutrients come in as well, lots of agricultural nutrients. The top slide on the right shows a plume of nutrient-laden agricultural runoff coming into Lake Mendota from Pheasant Branch Creek after a storm. And we have lots of algae blooms, and famously you can see them from space. So there's a Sentinel-2 image from the September 11th, 2018 blooms, and we get a lot of these. If you follow that website, you will, in summer, after about July 1st, you'll see a lot of blooms in Lake Mendota. The, we are seeing increases in phosphorus load, big phosphorus load events, as well as big precipitation events. So this graph is a bit complicated, but worth understanding. It's published in that paper listed below. So I've plotted precipitation return level against the phosphorus load return level for matched time series over from about 1974 to the present time. So lots of data go into this graph. And let's take, say, the 10-year storm. So look at the bottom x-axis, precipitation return time in years. Take a 10-year storm and read up to the precipitation return level, and that's about 100 millimeters. So the 10-year storm is about 100 millimeters. If you're an American, that's 4 inches. Europeans are going to have no trouble with that. So then read up the 100 millimeter line to the red fit, and you get around 10 to the 4th kilograms per day, about 10,000 kilograms per day of phosphorus from a 10-year storm. 10,000 kilograms is 1/3 of the median annual load in one day. That is a lot of phosphorus. So at the risk of pounding this point too hard, we're getting more bigger storms, and they're carrying lots of phosphorus and other chemicals into the lakes. And this is leading to lots of algae blooms. The North Temperate Lakes LTER site, led by Emily Stanley, now runs an automated buoy program in the lakes and collects phycocyanin data and other pigments and physical chemical variables every minute. And this has been going on since 2006, so we have tons of evidence of increasing cyanobacteria, this phycocyanin data collected by NTL LTER. And recently I've been using system reconstruction methods to try to understand the dynamics of the cyanobacteria. What's the underlying dynamical behavior? And from system reconstruction is a physical method that you can easily find in the literature. And it breaks the data down to a deterministic skeleton, an estimate, it's kind of like a regression estimate, but a different approach, and environmental noise in the red. And the deterministic skeleton looks exactly like the alternate state rate graphs that you saw in your textbook of systems ecology, if you ever took systems ecology. So it crosses the 0 line at 3 points. The lower and upper crossings are stable states. The intermediate, noisy one is an unstable state. The theory for these dynamics are very well known, and I can talk to you in more detail if you have questions about it. The integral of the blue line, simply integrate deterministic skeleton across its range. And the integral gives you something called the potential. The potential is a physical statistic of the potential states of the system, and this is a double well potential. So the left well and right well are stable states. The peak in between them is the unstable transition point. So the lake could be in the deeper well, the more stable well, which has very low phycocyanin. It's very clear water. Or it can be the upper well, which has 1 million times more phycocyanin and is highly eutrophic. It's extremely unlikely that the lake is going to be on the top of a hill. Potential diagrams work like gravity. The slightest disturbance and from that equilibrium at the top of the hill, and the ecosystem is going to fall into the left or right attractor. This is a time series. The gray line is the time series of detrended, decorrelated phycocyanin for 2017, and the red lines are the stable and unstable points. My point here is that the lake spends virtually no time in the unstable hill. Once it's in the unstable state, it moves very quickly into the other stable state. Very, very rapid transitions. And when I showed this data to friends in the social sciences in a meeting at Stockholm Resilience Center, they said, wow, that is really interesting because social systems take forever to change. They can change abruptly with things, civil wars or other big perturbations, but mostly they just struggle along and change very slowly. So what's going on with social systems? So with Carl Folke and Francis Westley, who study social change, we talked about what's going on with change in social systems, and are lakes a good analogy in any way? The model that we came up with based on the social system data was very different from the lake data. Social systems tend to stay on a plateau, a very fragile plateau of social experimentation and contention, arguing, before eventually moving into a new state. So we found from this review that the Earth system, of course, is in a very unstable state now. Human population cannot continue at present consumption rates. Climate is moving outside the range of our species' experience. Soil, water, ecosystems are degrading. None of those things go on forever. Something has got to give. The system has got to go through an unstable period and then shift into something else, hopefully not catastrophically. There are many emerging movements in society now that are driven by this perception of instability in the Earth system. In the United States, for example, the Green New Deal is now becoming prominent. It's highly debated, and I'm not taking a position one way or another, but it's very interesting that this controversy is becoming a big political issue in the United States at this time. And there are many other emerging movements and experiments. These offer lots of dangers. One of them is looking to the past to solve novel problems of the future. And there is, unfortunately, a fair amount of that going on. Another danger is embracing a shiny new idea before it is tested adequately. So when you have a shiny new idea that looks promising, the smart thing to do is do some safe experiments. Try it at small, reversible scales, see if it works. If it seems to work, scale it up. We have lots of opportunities right now to develop verifiable ideas that could help sustain global civilization. And sustaining global civilization is hopefully something that we all are in favor of. But during this period of transition, the social research shows that we should expect high variability, many alternate pathways, some of them bad ideas, some of them good ideas, and the outcome is very uncertain. And it's a very uncomfortable time, and we're in that time now. Scenario thinking has emerged as one of the ways to engage scientists in thinking about social change. And I first learned about this when I was one of the co-chairs of the Millennium Ecosystem Assessment, which was a global project to look at how ecosystems might change out to 2050. And we developed scenarios for changes in the Earth system over the 50-year period from 2000 to 2050. You can read about them in published volume. These are now pretty familiar. And we found that it was a very powerful method. We had very useful conversations with leaders around the world about what is going on with planetary resources. One of the things we discovered in this project is that there are lots of disaster scenarios, for how the world could collapse. This is one of our disaster scenarios that we put a lot of analysis into and a lot of modeling. And at the time, I thought this would never happen. We just needed it as sort of a reference point for the more positive scenarios. And I had no idea it would turn out to be the bumper sticker for a major political party in the United States now, with the wall separating rich and poor. We really didn't think it would happen. What we're short on, what we need a lot more of, is feasible ideas for positive futures. Michael Mann had a tweet in a Washington Post article about that on Sunday, and Michael Mann said, "Doomsday scenarios are as harmful as climate change denial." And if you follow him on Twitter, you can find out a little more about what he meant there, and I agree with what he's saying. Another limnologist, Elena Bennett, has now leads a project called Bright Spots, Seeds of a Good Anthropocene, that is a global group of social and natural scientists looking for current practices, innovations and experiments that could put global civilization on a sustainable path. So once again, a limnologist shall lead them, as John Cole would have said. And this is an amazing and remarkable project. I've got the URL up there. And Elena has given two really great presentations you can find on YouTube. One is her presentation to the World Economic Forum in Davos about the Bright Spots project. And another is her TED Talk. So if you want to get cheered up for the day, take a look at one of those talks. You can also scale scenario thinking down, and we have applied scenario thinking to the Yahara watershed of the Madison Lakes. We used a similar social engagement process. These scenarios were developed with a lot of outreach and workshops with the public and surveys of the public. Again, we developed 4 scenarios. I don't have time to go through these in detail, but we also engaged artists. There's a lot of art. We wrote all of the scenarios up in highly readable form by real journalists. People like me did not write them. Technical people didn't write them. Journalists wrote them. And we made videos of each story, and we had a writing contest where people submitted short stories about the future of the Yahara. You can read all of that on the website here. Another successful application of scenario thinking that brings in scientists, but also brings in the general public, social scientists, a great diversity of people to simply talk about the future. What do we want the future to be? And those discussions are constrained by scientific reality. Constrained and informed, I should say. So let me try to wrap up what I've said. I've covered a lot of material here. Rapid change in the Earth system is shifting paths of ecosystem change, and all of you know that, and I bet everyone in this room works on some aspect of that statement. Ecosystem research, such as the whole lake experiments that I showed you at the beginning of the slides, ecosystem research has validated nonlinear models of ecosystem transitions from one stable path to another by crossing an unstable plateau. And these discoveries are transforming environmental economics. Economists are paying attention to abrupt nonlinear change in a way that they have not before, largely as a result of lake research. And so we can be proud of what we have done there. The global system of Earth and society is now on an unstable plateau. And an unstable plateau it's kind of like walking on a volcano. It can be sort of an uncomfortable place to be. But the unstable plateau is not the end of the world. Unstable systems are changeable systems. Every system that undergoes change goes through a period of instability first. And we now have an opportunity to change toward a better planet. So in a way, it's good news, but it also tells us we have a lot of thinking to do. So now's the time for open conversation about future paths that could share Earth resources and sustain more than 8 billion people and life on Earth. Scientists, especially environmental scientists and water scientists, we're not going to have a sustainable future without water resources. We're absolutely critical to these conversations. And I was really happy to see Jen Tank's talk. I'm really happy to see some of the outreach and public engagement sessions here at this ASLO meeting to enable us to talk with each other about how to do this better. I think the scenarios of the Millennium Ecosystem Assessment and some of the local scenarios that have been tried are another great example. And we need more of this, and it's going to take environmental science and water resource science. So young people out there should get busy, and fortunately, you have a guarantee of lifetime employment due to these global problems. So all of us need to get busy, and I plan to stay busy working on these things. Well, something happened to my last slide. Let's try that one. Oh, there it is. There's my last slide. I'm done. There are 3 minutes and 8 seconds for questions. Or I will just get out of the way and let the next thing happen. Thank you all very much.